This is number 4 off of the AP FRQ review for Riemann sums. The height of a tree at time t is given by a twice differentiable function. Again, this just means a smooth curve. We're not going to have any sharp turns. Where h of t is measured in meters and t is measured in years, and selected values of h of t are given in the table. So at certain time periods, we're given information about the height of the tree. And so for part A, it says estimate h prime of 6. So h prime of 6 must mean the rate of change of the height, the change in height in meters per year at the 6th year. So what is the rate of change of the height of the tree at the 6th year? So if we want to find rate of change, we don't have a function that allows us to find the derivative, so the best that we can do is to find slope, find the rate of change. And if we want to find h prime of 6, we're going to use the two closest piece of information, 5 and 7. So we're going to figure out the rate of change of the change in height between the 5th and the 7th year. So we can say change in height over change in years, 11 minus 6 over 7 minus 5. And that gives us 5 over 2 meters per year. So approximation based off the table of values, it's about 2.5 meters per year is the rate of growth on that 6th year. Part B, explain why there must be at least one time between 2 and 10 where h prime of t is equal to 2. How can we guarantee that there is a rate of change of exactly 2 between 2 and 10? Well, this is applying mean value theorem, which says that if the rate of change between 2 and 10 happens to be 2, then we can guarantee that because it's a twice differentiable function, there must be a rate of change of exactly 2 that sits between the endpoints. So let's see if that is true. And we did see between h of 5 and h of 3, okay, between h of 5 and h of 3, we're able to, if we kind of look at some of these table of values, we're able to see that 6 minus 2 over 5 minus 3 is 4 over 2. This gives us a rate of change of 2. So therefore, we can guarantee that because there is some place there's a rate of change of 2, there must be an exact rate of change of 2 somewhere between. Okay? So that's by mean value theorem. Okay. There must be at least one time between 2 and 10 where h prime of 2 is equal, h prime of t is equal to 2, and that's based off mean value theorem, which says that f prime of c, the rate of change, we can guarantee the rate of change as long as we have an average rate of change between those two endpoints, between any two endpoints. For part C, use trapezoidal sum with 4 subintervals to approximate the average height over the time interval. So we don't want to find the height, we want to find the average height. So let's think in terms of average value theorem. Okay, so average value theorem is 1 over b minus a, integral from a to b of, in this case, h of t dt. Our a and b values are 2 and 10. Plug that in, 1 over b minus a, 1 over 10 minus 2, from 2 to 10 of h of t dt. So that's 1/8. And we want to use trapezoids between 2 and 10. So we have a width of 1, a width of 2, a width of 2, and a width of 3, simply by subtracting the values in the t from years. And each of the areas we have to use width over 2 times height 1 plus height 2. So our formula for trapezoid is width over 2, height 1 plus height 2. So just looking at these table of values here, we have first trapezoid has a width of 1, so width 1 over 2, 1.5 plus 2. Second subinterval has a width of 2, so width over 2, so 2 over 2, 2 plus 6. Third subinterval, 2 over 2 times height 1 plus height 2. And then third subinterval, last subinterval has a width of 3. So 3 over 2 times 11 plus 15. So it's a little messy with all these trapezoids, but we can use our calculator to evaluate all these separate areas. And this will give us the definite integral from 2 to 10 of h of t. We divide that by 8, and that gives us our average height between years 2 and 10. All right, now part D is a messy part here. It says the height of a tree can be modeled by the function g, and g of x is given as 100x over 1 plus x. X represents the diameter of the base of the tree in meters. Okay? When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. According to this model, what is the rate of change of the height of the tree with respect to time? That's a big hint there. In meters per year at the time when the tree is 50 meters tall. Now we're dealing with time here. We're dealing with the rate of change with respect to time. So this is going to be a related rates problem. And what that means is that we're going to be involving derivative, but with each of the derivative, our variables are all going to be affected by time. So we're going to be seeing some dg over dt, we'll see some dx over dt. Each time we find a variable's derivative, we're going to have to attach a d over dt. So it says the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So we can do a little bit of information gathering. So we can say dx dt, right? If x is the diameter of the base of the tree, then dx dt must be the rate of change of the diameter, which in this case they tell us is 0.03. According to the model, what is the rate of change of the height of the tree? So we're looking for dg over dt, because the height of the tree is represented for part D as g. So we're looking for dg over dt. So let's look at our g function and work from there. Okay. So we're going to find dg dt, and we have this function to begin with. G is equal to 100x over 1 plus x. So let's take turns finding each of the derivatives. G is just hanging out by itself, so G just becomes dg dt. Now if I want to find the derivative of a numerator and denominator, I have to go through quotient rules. So f prime g minus f g prime all over g squared. Okay, so let's start with f prime. F prime for 100x is 100 dx dt, so that's my f prime, times the g function, minus f, which is 100x, times g prime. So g prime is the derivative of 1 plus x. 1 goes to 0 and x becomes dx dt. All over my denominator squared. 1 plus x quantity squared. Okay, we have the derivative. We're looking for dg dt, and now let's see what we can plug in. Okay, we have dx dt, right? We found that from gathering information from part D here. Part D says that dx dt is 0.03, so we'll plug in 0.03 for dx dt. And I think the only thing that we need other than this is we don't have the x value. Okay? We don't have the x value, but we do have something related. We do know that this, we're looking for a specific diameter at a specific moment in time. And that moment in time is when g is equal to 50, right? They keep saying in the problem that we're talking about the moment in time when g is equal to 50, when the height of the tree is 50 meters tall. Well, if we know the height of the tree is 50 meters tall, we have an equation that relates the diameter with the height of the tree. So if I plug in 50 in for g, I can cross multiply and go through my algebraic steps to solve for x. That's a little cumbersome having to go through all these steps here, but we're kind of walking through the steps now. So if I plug in 50 in for g, I cross multiply, I get 50 times 1 plus x, which is 50 times 1 plus 50 times x. It's equal to 100x. Subtract 50x from both sides, I get 50 equals 50x, so x equals 1. So when the height of the tree is 50 meters, we know the base of the diameter is 1 meter. So I plug in 1 for all the x's. plug in 0.03 for all the dx dt's, and we clean this up, and this cleans up all the way to be 3/4. We know that dg dt is the rate of change of the height of the tree, so we know our answer is going to be in terms of meters per year. So when the height of the tree is 50, the rate of change of the height is 3/4 meters per year.